Hello everybody. In this video I'm going to show you uh, some of the example from chapter 4, and we'll be working on 2D cases only. Okay. In the next video actually I'll show you the 3D problems. Okay. Now before I start the example problem, let me summarize the theory that what you already learned from the other video. Okay. Now let's say for 2D case, if I have a point here, let's say this is a overhanging beam and you have a force working there which is F here, which is making, let's say, 30 degree with the horizontal, and the force is 100 pound. So if I want to find out the moment at this point, any point like here at A, then the moment at A would be equal to force multiplied by the distance. Okay. Now that distance is very important, that what distance we are talking about. So the distance would be the shortest distance or perpendicular distance from point A, means like at which I'm trying to take the moment, to the line of action of the force. Okay, to the line of the action of the force. So if you see here, that's basically, if you draw the line here, then basically you have to extend this line here. This is the line of action of that force, and if you take the perpendicular distance of that, then this basically we are talking about this distance here. Okay, so D is the shortest or perpendicular distance from the point at which I'm trying to take the moment to the line of action of the force. Okay, so many times you will see when you're trying to find out the shortest distance, actually it doesn't touch with the forces, so you have to extend the line of action of that force to find out your distance. Okay, that's the first thing here. Now if the size of the beam is 10 feet, so you can see this one would be, this one D would be equal to 10 sine 30, which is actually 5. Okay, and the moment at A is equal to force multiplied by D, which is actually 100 multiplied by 5 equal to 500 pound-feet or feet-pound, whatever you say. Okay, that's the one way to do that. But sometimes it's very difficult to find out that shortest distance like that. Okay, that then I have to just extend a lot of forces, like the line of action, and that makes a little bit, like clumsy. So rather than doing that one, sometimes the way, or most of the times, the way we try to solve that one is like this way. Actually, we are gonna get the same answer here. Just try to remember this is 500 feet-pound, okay? So the way we usually try to do is actually we dissolve that force into two components. So you can see that so this one is actually 100 cosine 30, and this one is 100 sine 30. So just for clarity, I'll just take this one off here because I already showed the two components of this one. Now you can see here that the force 100 cosine 30 is actually, the line of action is actually going through point A. This means like the shortest distance from A to the line of action of that force 100 cosine 30 is equal to 0. Okay? So let's say this is F1, 100 cosine 30, and D1 is basically 0. Now if you think about this force here, that's actually F2, which is actually 100 sine 30, which is actually 50 pounds, and that perpendicular distance along the line of axis of that force is actually 10 here, right? You can see this is perpendicular distance from A to that line of force. So actually your D2 is basically 10. So if you take the moment of the two forces, actually this one is 0, and then your moment at A is basically 100 cosine 30, which is actually 50 multiplied by 10, which is 500 pound-feet. So you get the same answer here. So most of the time actually what we do, we dissolve the force into two components and try to see in such a way that the distance is already, like given there, so that you don't have to find out the shortest distance or anything like that. Okay, I'll just show the example that what I actually wanted to mean here. Now, one of the most important thing would be to know whether the moment is working clockwise or counterclockwise. Okay, clockwise or counterclockwise moment. Let's say this is our point A here, and I have a force here, let's say F. The way I try to do that one is like how this force is trying to rotate along this point A. Okay, so what I have to do, go to the head. It can go either like this way or it can go like this way. Now you see that in which cases actually it's gonna rotate around point A. So definitely this is the way it's gonna rotate along the point A. So this one is definitely a clockwise direction movement. But for the same load, but same force, if I take a moment at point somewhere here, B, then you can see this one is rotating, this one is now rotating along point B. So it's very important that which point you are taking the moment, okay? So the force has to move around that point, okay? So if I take a moment for B, now you can see that's actually the way this one tend to rotate, okay, like this. Now this is definitely a counterclockwise moment, okay? Sometimes you will see that your force is far distance from the point, and it's a little bit difficult to find out whether this one is clockwise or counterclockwise. So in that situation, you can just move the force along the line of action of that force. For example, let's say I'm trying to take a moment at point A for a force here. Now it's kind of difficult to see like whether this one is like rotating this way or this way, right? So it's always better, to draw the line of action of that force and move that one here, okay? And try to see whether the force is rotating clockwise about the point at which I'm trying to take my moment, or the counterclockwise way. So you can see if you want to include that point, then basically you are going to in the clockwise direction. Okay? Now, what I said, like let's solve some problems so that we can understand actually what we have to do. So here, actually I already trying to do problem number 4-8. So 4-8 is saying that determine the moment of each of the three forces about the point here. Each of the three forces, you can see one force here 250 Newton, the other force is 300 Newton, and this is 500 Newton. I have to find out the moment at point B. Now basically you can see that this force is actually going through point B. So the perpendicular distance from B to the line of action of this force is equal to 0. So in the moment you don't have any effect of this force here. Okay? Now what I have to do here, I'll just try to dissolve that force into two components. Okay? So this one has to 300 cosine 60. 300 cosine 60. Let me 300 cosine 60 and 300 sine 60. Similarly, I can dissolve this force here too. That's 250 cosine 30, and this one is actually 250 sine 30. Okay, so now we have to find out the moment for each of the forces, the force F1, F2, and F3 at point B. Now, from the observation, you can see the force F3 is basically passing through the line of action of that force. F3 is passing through B, so basically the distance is 0 from B to the line of action of F3, and the moment for this one would be 0, right? So let me write it down from there, that moment at B for, let's say, for force F3. So that has to be 0. Okay? Now let's for force F1. Okay, now you can see for force F1 I have two components here, 250 cosine 30, which is going this direction and vertical direction, and if you try to see that how this one is rotating, Then basically, let's say, write it down, that summation of moment at point B. Let's say counterclockwise is positive. Okay? Counterclockwise positive. Definitely you can assume clockwise is positive. That's up to you. And at the end, if you get a positive number, then I'll just say that yes, my moment is counterclockwise. If I get a negative number, then basically I'll say no, it's actually clockwise, like moment. Okay? So here for B, if you see, this force is actually moving around this, right? Along B. So this one is basically counterclockwise, so positive. So this is 250 cosine 30. And then you can see the line of action of that force is going like this, and the distance from B to this line of action, or the shortest distance, is actually from here to here, which is actually from here to here. That's actually 3 meters. Now you can see this one is actually trying to rotate that one like this, right? If you just go and try to rotate along that point B, which is basically clockwise, so I'll just put that one negative sign because counterclockwise is positive. Then you can see 250 sine 30 into the distance of that force, which is actually the line of action of that force is here, and the shortest distance is 4 meters. So that's basically 150 Newton meter. Okay? Now if I try to do that one for force F2, then you can see F2 has two components now. This one is just, this component is going, the line of action of this component is going through B. This means like the distance from B to the line of action of this component is 0, so it doesn't have any moment. So only moment I have is this one here, okay? This one. Now if this one wants to rotate about point B, this one has to go like this, right? Or it can go like this, but if it goes like this, that basically doesn't include point B. So this one is negative sign, so moment at B would be equal to 300 cosine 60 multiplied by the distance, which is from here to the line of action of this one. This is like the perpendicular distance, so the distance is 4 meters. So that's actually 600 Newton meter. So that's the answer. Okay? Now let's move forward. Now I am gonna show you the problem number 4-12. Okay? This problem is not that difficult, but you need to do a little bit more geometry. Okay? What this problem is saying, that the tow line exerts a force of P 6 kilonewton. Okay? And at the end of a 8 meter long crane boom, so this is your crane boom, which is 8 meter long. Okay, I just simplified the drawing a little bit. Now they are asking that if X, this one is working like 6 kilonewton, and this one is like, let's say, point B here. And they're saying the distance from here to this point B is 10 meters. Okay, so determine the position of this boom, like theta here, okay? For what? Which will create the maximum moment at point O, which will create maximum point at O. So we have to find out the theta at this time, the moment would be maximum, okay? Now I try to draw that one here. This is your boom, which is 8 meter long, and this is my point B. And I had that force 6 kilonewton working here. Let's say this angle is phi here, okay? Just I'm assuming this angle is phi here. So I can dissolve that force into two components. One is 6 cosine phi and 6 sine phi. Now you can see that 6 cosine phi, the line of action of that force is passing through the B, so it doesn't have any moment, okay? Now I have moment for this component though, and this moment would be this force multiplied by the distance from here to here, because this is the perpendicular distance, okay? So in that situation, you see that your moment here is actually 6 sine phi multiplied by 8, which is 48 sine phi. Now they are saying that what would be the maximum moment, okay? So you can see if you change your phi from, let's say from 0 to increase that one, you will see the maximum would be when? Sine is maximum when sine phi equal to 90, right? So when phi equal to 90, that time you have the highest moment. So if you plug that value here, that would be actually 48 sine 90. That's actually 48 kilonewton meter. So you already have the answer. Now, they are asking, like, at that situation, what would be your theta? Okay? So I draw that one here. Okay, that when this one is actually 90 degree, then what would be this angle now? Okay, so to do that, first of all, let me find out this angle here. This is actually, let's say this is gamma. That would be, gamma would be tan inverse 1 divided by 10. That's actually 5.71 degree. Okay, so since this line and this line is parallel, so this one is also your gamma here, okay? Now you can see in the triangle ABO, if I use the sine rule, then you can see 8 divided by sine beta is equal to this one, BO, which is actually, let's write that one, BO divided by sine 90, which is actually 0, but you can find out the BO because you know this one and this one, so your BO is basically from the Pythagoras formula, 10 square plus 1 square, that's actually root over 101, okay? So I can plug that value here. Root over 101 divided by sine 90 equal to 1. So if I solve for beta, so that would be basically sine inverse 8 divided by 101. That's actually 52.75 degree. So you can see then alpha would be, because this is 90, so alpha would be 90 minus beta. So which is actually 37.25 degrees. Okay? So alpha would be 37.25. So what would be theta here? So theta would be alpha minus gamma. Okay? So theta is basically alpha minus gamma, which means 37.25 minus 5.71. That's equal to 31.5 degree. Okay, so theta has to be 31.5 degree. Now let's move forward. Problem number 4-16. Okay, the problem is saying that if a man at B, actually B here, someone is here pulling that one with a force P equal to 30 pounds. This one is 30 pounds here. Okay. Determine the magnitude of force F the man at C is pulling here, so that the resulting moment is 0 at point A. So you have to find out the force F so that the resultant moment at A equal to 0. Okay, so let's take a look here. So first of all, what we have to do, dissolve the force into two directions. So you can see if this is 45 degree, this is also 45 degree. So if I dissolve that force here, so this one has to be this is 30 sine 45 and this is 30 cosine 45. Similarly, I can dissolve that force into two components, right? The horizontal component would be 4/5 and the vertical component would be 3/5. So that's 4/5 of F, and this one is 3/5 of F. Now you can see like this component and this component is passing through point A. So basically the distance from A to the line of action of these and these two vertical forces is actually 0, right? Now I can just take a summation of moment at point A and let's say clockwise is positive, okay? So you can see for this force, actually this one is going to rotate like this, right? So that's a clockwise moment. So the force is 4/5 of F multiplied by the distance, which is 12 here. And you can see this force is actually going like this. Okay? It can go either like this or go like this. But if you want to include point A, then it must have to go like this. Okay? So which is counterclockwise. So this one 30 sine 45. And the distance from here to here is actually 12 plus 6. That's actually 18. And that has to be 0 because the resultant moment has to be 0. Okay? So if I solve for my F here, then you can see 4/5 of F into 12, that's actually 30 sine 45 multiplied by 18. So F equal to sine 45 into 18 into 5 by 4, and then here is actually 12. So F is basically 39.8 pounds. Okay, let's move forward. Problem number 4-20. Okay, the problem is saying the handle of a hammer is subjected to the force of 20 pounds. Determine the moment of the force about the point A. Okay, so here is the figure. I just simplified that hammer here, and they are showing that this one is 20 pounds working here. You have to find out the moment at point A. So there is just one force here. You can dissolve that force into two components, this way and this way, because the distance here and here is given. Okay, so to do that, let's try to dissolve that force, 20 pounds. So this one has to be 20 cosine 30, and this one has to be 20 sine 30. Okay, so if I take a moment at A, summation of moment at A equal to, let's say clockwise is positive. Okay, clockwise is positive. So if I think about point A and this one, you can see this one can rotate like this clockwise. Okay, so that would be 20 cosine 30 and the distance. So distance from here to the line of action, actually the same distance here, right? So this distance is actually this distance, which is actually 18 inch. Let's say 1.5 feet. Okay? Or you can just keep that one in inch too, that's up to you. Now, for this one, you can see like the other one, whether this one is negative or positive, but you can see this is the line of action of that force. So if that bring that force here and this one has to rotate around A, the only possible way is like the clockwise rotation. But you see the clockwise is positive, so I'll just take that one positive. 20 sine 30 multiplied by the distance. So you can see the distance from here to here to here is actually 5 inch. So if I solve that one, that's basically 362 pound inch, right? If I change that one to feet, then basically I'll get that 1 pound feet. So both are correct because you can put that one either inch or feet. Okay, now you can see one more thing here, that you assume clockwise is positive and you got a positive moment here. This means like the actual moment is clockwise, right? So we can just write that one clockwise. If you don't write that one, that's also fine because I assume that one is positive at the beginning. Okay? Now let's move forward. Problem number 4-24. Okay? This one is showing actually a crane, tower crane here. This is your tower crane and this is the smaller arm BC and this is the longer arm BD. The weight of that arm BC is 0.4 megagram. Megagram means like 10 to the power 6 gram. Okay, and the weight of this one is actually 1.5 megagram. Now this one is trying to pull a weight which is actually 2 megagram, and you have to find out what would be the counter weight here so that the moment at A would be the resultant moment at A because of all that 4 forces would be 0. Okay, so I have the distance for each of the forces here. Actually these are mass because it's in grams, so you have to multiply that one with 9.81 to make that one force, because your moment is always in terms of force, right? So to do that, let's say I'll just try to find out the summation of moment at A. Let's say this is positive, clockwise is positive. So first of all, this one is definitely these two will rotate clockwise and these two will rotate counterclockwise, right? Let me assume counterclockwise is positive, that would be easier to do. Okay, so I'll start from this one. You can see the moment for this one is W, or I can keep that one W, that's fine, multiplied by 7.5. That's the distance from A to the line of action of that force. Okay, so the line of action of that force is passing here, and the distance from A to the line of like action of that force is this much, which is actually 7.5 meter. Okay, so plus for this force, so 0.5, or I can just change that one to kg, right? Let me change everything to kg. Let's say this is m. So I'll just say this is a mass in kg into 9.81, and then the distance 7.5. Okay, so this many kg. Then this one is actually 500 kg into 9.81, and then the distance is 4. Now you can see the other side, this one and this one is trying to rotate that one clockwise, so both of them would be negative. So for this one is actually 1500 kg into 9.81, and that the distance is 9.5, and this one is 2000 kg into 9.81 into the distance 12.5. And they are saying that resultant has to be 0. Okay? So if I rearrange that one, then basically you will see m is equal to 1500 into 9.5 plus 9.81 into 12.5 minus this one I'm taking to the other side, 500 into 9.81 into 4. Okay, so if I solve for m, then basically m would be equal to 4970 kg, which is basically 4.97 megagram. Okay, this means like if the counterweight is 4.79 megagram, then the moment in this direction will be counterbalanced by this direction. Okay, so the overall moment at point A should be 0. Thank you for watching.